Well, good morning, kids. It is 11:12 on Wednesday morning, April 15th. So if you hear some random noise in the background, it's because they're doing some work on an HVAC system in my house, so there's nothing weird going on, just some random industrial noise. So let's talk thermodynamics, which is the next big unit. A lot of this will be review for those of you that have had physics or Chem 2. Some of the math will be a little bit new in terms of how we do some calculations. So let's start with the big idea that when you're talking about temperature, okay, remember temperature, degrees Celsius, a lot of times we're going to work in Kelvin. And remember to make that conversion, you just add 273 to it. So, but temperature, remember, is just a measure of the kinetic energy of the particles, okay? So just because you have an oxygen molecule that has a very high temperature, meaning that has a lot of kinetic energy, that doesn't necessarily mean that there's a lot of heat in the room. So like the classic example is that you light a match, okay? And if you put your hand on either side of that, okay, you're going to burn your hand because these particles have a very, very high kinetic energy. But you're not going to have very much heat. So this temperature, we're measuring in 273. Typically, we measure with a thermometer. And basically how that thermometer works is that there's a liquid in there or there's some type of sensor. And as these particles gain more and more kinetic energy, either the level goes up because they're occupying more and more space. So it's kind of like second graders. And if the second graders are cold, they all kind of bunch together, okay? But if it warms up at like 80 degrees, then those are going to have more kinetic energy, and they're going to move apart, and that's going to push that level up. So temperature, measure of kinetic energy. So when you look at what we can measure quantitatively, we can quantitatively measure temperature, but it's difficult to measure heat because heat is a measure of the total amount that's in the system. So one of the things we can use Q equals M delta T, C sub P. Now, for those of you that have heard me give this lecture in physics, this is the chemistry lecture. So the mass is going to be in grams. Typically, your change in temperature is either going to be in degrees Celsius or Kelvin. It doesn't make any difference because this is the change in temperature. Keep in mind, this is the change in temperature. And then you have the specific heat, which is the energy needed to cause 1 degree change in Kelvin or 1 degree change in Celsius or Kelvin, doesn't make any difference. And that has units of joules per gram degree Celsius. Now, sometimes you'll see this in chemistry, especially instead of joules per gram degree Celsius, sometimes you'll see it written as the molar heat capacity, which is the same idea, but it's joules per mole degrees Celsius. So it's the same idea. So if you have like 1 mole of helium gas, okay, or whatever it is, this is how much energy is absorbed or released when this thing undergoes 1 degree change of Kelvin or Celsius. So in some ways that makes it easier, especially with gases, because it's tough to measure like 1 gram of a gas because it's such a small quantity. So a lot of times we'll talk about moles. So, and it's a simple conversion. So like if you have joules per gram degree Celsius and you want to change that into molar heat capacity, that you just put like, let's say for example, you have, I don't know, magnesium. Okay, so let's say that's joules per gram degree Celsius. Well, magnesium is 24.3 grams per mole. So the grams would cancel out. You would get joules per mole degree Celsius. So if you have grams or joules per gram degree Celsius and you're asked to find that molar heat capacity, just change it to joules per mole. It's a simple conversion. Y'all have done that before. So here's going to, and this is all in your lecture notes. So you also have to differentiate between the system and the surroundings. So one of the things you'll do is like you're going to have a cup of water and you're going to add something to it. So the water is going to be the surroundings. And what you add to it is the system. Okay? So here's going to be the main idea, that energy lost has to equal energy gained. So what we can't do is we can't look at necessarily what's happening with the system, because we can't observe individual bonds that are being broken or formed or anything like that. What we do is we look at what's going to happen to the surroundings. So if this is going to be the calculation for the surroundings, so that's going to be the mass times temperature final minus temperature initial times the specific heat. So let's talk about the mass part of this. If you're dissolving a salt, and this is going to be in a couple of problems on the assignment. So let's say that you dissolve 1 gram of salt into 25 grams of water. So the mass that you're going to use is going to be the total mass, because that salt is going to be dissolved in the water. Now, if it's like a chunk of iron, don't add the iron to this, okay? Because the iron isn't going to dissolve in the water. So anytime you have, and there's a couple of problems on the assignment, like I think there's like ammonium nitrate and I don't remember what else. But anyway, and this is what you're going to see in the lab tomorrow. So anytime something is going to dissolve and actually become part of the system, you add that mass to it. Now, here's what's going to be important. So let's say you're at 22 degrees Celsius and you run this reaction and it warms up to 24 degrees Celsius. So that means that your change in temperature, 24 minus 22, is going to get you a positive number. So that means that the energy gained by the surroundings is equal to the energy that's lost by the system. Okay? So since this is going to be a positive number, because you have a positive mass times a positive change in temperature times a positive specific heat, this is going to be a positive value. So that means the energy lost has to be a negative value. So typically this is what we observe. So we can't directly what's happening with the system, but we observe what's happening in the surroundings. So once we figure out what's happening in the surroundings, whoa, that got weird. Okay, I just randomly moved in orbit. So once that happens over here, and once we figure out what's happening over here, so this is like a positive value, that means it's going to be a negative value for the system. And that's typically what we focus on. So listen to me very carefully. We observe the surroundings, but what we focus on is on the system. Now, if the converse happened, let's say that you start at 22 degrees Celsius and you dissolve some salt in it, and the temperature drops to 20 degrees Celsius. That means that you're going to have a negative value for the surroundings, which means the system would have the opposite sign. So listen to me very carefully. When you're doing this, the system, in terms of Q, has the opposite sign of the surroundings, because energy lost is going to equal energy gained. But this is what we typically focus on. Now, that leads us to an idea of enthalpy. So enthalpy is represented by delta H. And you have two potential things in terms of your delta H. So delta H can be positive or delta H can be negative. And it's joules per mole, okay? Or sometimes you see it kilojoules if you're dealing with big numbers. So on your enthalpy, so notice that you have energy here just like you have up here, but it's per mole. So what you're going to do on a couple of these problems in the lab tomorrow is that you're going to calculate the value of Q, which is going to get you your value of joules. And then you're going to divide that by the number of moles. Okay, like for example, I think you have a problem with ammonium nitrate, I think. So to get your enthalpy, you're going to calculate your delta H, your energy, and then you're going to divide that by the number of moles of the salt. You don't include the water in this calculation. This is just going to be the ammonium nitrate or whatever that is actually dissolving. Don't include the water in this part. So if you have a negative delta H, that means it's an exothermic reaction. If you have a positive delta H, that means it's an endothermic reaction. Okay? So this is where, like, the magic happens. So if you go back up to where we started, you dropped something into a container of water, dissolved salt, you add salt, and you increase the temperature. That means Q for the surroundings is going to be a positive value. So that means Q for the system is going to be a negative value. And then if you take that Q and you divide that by the number of moles, then you get a negative delta H. If the temperature had gone down, Q for the surroundings would be a negative number, Q for the system would be a positive number, and then you'd have a positive delta H. So this is all about the signs, okay? Listen to me. This is all about the signs. Okay, now, let's talk about delta E. Now, for those of you that have been through physics, you have seen this written as delta U. Delta E mean the same thing. This is the change in energy in the entire system. So that equals Q plus W. So Q is the energy that flows in or out of the system. So if you have a positive Q, that means energy is flowing in. You would see the temperature go up inside the container. If energy flows out, you would see temperature go down. So if energy is added to the system, Q is a positive number. If energy flows out of the system, Q is going to be a negative number. That one's fairly simple. Energy in, energy out. Now, the W stands for work, okay? Quick refresher, okay? To do work, you have to exert a force over a distance. So, work, there's two ways you can deal with work. One is just given to you, the other one that you calculated. So here, this is all about the wording of the preposition. So if you have a syringe, and ideally I'd demonstrate this, and the volume gets bigger, okay? So work is going to equal negative P delta V. P is your pressure. Now, this is where this gets a little bit weird in terms of the units. Typically in a chemistry class, this is going to be measured in atmospheres. So this would be like -1 atmosphere. Typically your change in volume, which is going to be volume final, volume initial, is going to be in liters. So this is what's going to be different. In a chemistry class, not a physics class, work is typically measured in atmosphere liters, okay? Not joules. Now, there is a handy-dandy little conversion, which we'll get into, okay? We'll get into this conversion in just a second. But one of the things that you want to begin to look at is the fact that when you're dealing with chemistry, this work could be in atmosphere liters, not necessarily joules. Now, there is a handy-dandy conversion, it's on your lecture notes, that 101.3 atmosphere liters is equivalent to 1 joule. That number is there, it's 101.3, it's like the radio station, 101.3. So that's how you can convert from atmosphere liters into joules. So this is where the magic happens. So let's say you're under normal atmospheric pressure, you're at 1 atmosphere. So if the volume gets bigger, so let's say that you go up to 2 liters, okay, and the initial volume was 1 liter, okay, then your work is going to be a negative number because you're going to have this negative sign out here. So that's going to be the importance of that negative value. Now, if the volume becomes smaller, you compress it, work is done on the system. So if the volume gets bigger, okay, you have negative work, and we say that work is done by the system. Okay? Now, if the volume decreases, then that means you're going to have positive work, and work is done on the system. Now, ideally what I would show you to demonstrate this is like a gas, it's called a gas syringe, where you have a syringe and you put like a little piece of cotton in here and you've slammed this syringe down and this little piece of cotton will catch on fire. Some of you that have went through physics might have seen this or remembered that. So what's happening is that because delta E equals Q plus W, so we're going to leave the heat transfer in and out of this thing. We won't worry about that. But because of the fact that we're decreasing the volume very, very rapidly, that means that we're doing positive work. That means you have a positive increase in your internal energy, and that's what makes that little bit of cotton catch on fire and ignite. So this is one of the things that you just have to know. Okay, you just have to know this. And for those of you, like I said, for some of you, this is going to be review. You've heard this lecture before. The only thing is that we're going to change the units a little bit. Okay, so let me see. Let's talk this value of delta H. So let's say, for example, that you have 2H2 plus O2 yields 2H2O. And you might be told that delta H equals, I'm just going to make up a negative 150 joules per mole. So what this means is that when hydrogen and oxygen combine to produce water, you have delta H, which is negative. Now, you all have seen this. You've seen an oxygen balloon blow up, okay? And it releases a lot of energy. A lot of heat is given off of this. So this is why this delta H is a negative value. So what this means is that this is 150 kilojoules per mole. So it's either per 2 moles of water, per 1 mole of oxygen, or per 2 moles of hydrogen. So what that means is that you can do stoich with this. So let's say, for example, you have, 4 grams of hydrogen. And I want to know how much energy is going to be given off if I combust 4 grams of hydrogen. Okay, well, if I got 4 grams, I know the molar mass of hydrogen is 2. That's per 1 mole, okay? So at this point, I know I've got 2 moles of hydrogen. So then I come over here and go, okay, that's 150 joules per 2 moles of hydrogen, okay? Then my moles of hydrogen will cancel out. So I take 2, so this is going to reduce down to 2, and that's going to cancel that out, so I'm basically going to get 150 joules. So if I combust 4 grams of hydrogen, okay, all I did was just reduce this down. Yes, it's called mental math. Stunning, I know. And you get 150 joules. So if you don't believe me, have Danae run the numbers on the calculator, and you can verify that. Because 2 times 2 is 4, that cancels out. So if you were doing this with the oxygen, then you would put 1 mole of oxygen down here. That's the only difference. So this is, if this is negative, that means this reaction is exothermic. If this had been positive, that means that it's just going to be an endothermic reaction, which would get really weird, because if this was positive, that means that we would blow up an oxygen balloon, or blow up a hydrogen balloon, and instead of feeling a rush of cold air or of warm air, you'd feel a rush of cold air. And it's like, oh, hey, it's cold. Let's blow up some oxygen, or it's too hot in the room. Let's blow up some oxygen balloons, and there you go. Anyway, so there's that. Those are the big ideas. I've got the lecture notes that I have sent out. And on these problems, especially when you get to like questions 8 and 9, make sure that you add the mass of the salt to the mass of the water when you're doing those calculations, and pay attention to the sign. So when you get to number 9, and this will make sense when you get to number 9, you're told that the delta H is negative 81.5 kilojoules per mole. And here's your equation. It's calcium chloride turning into calcium ions into chloride ions. Okay? So what this means is that when you dissolve, and this will, when you read the problem, we're dissolving calcium chloride into water. You have negative delta H. This reaction is going to be exothermic. The temperature of the water is going to go up. So this is all about switching signs. So you're told that you have an 11-gram sample of calcium chloride. You're going to change that into moles of calcium chloride. Then you can multiply that by this number, and then you're going to get up in kilojoules. Okay? Once you get into kilojoules, then you can go, okay, then you're going to know your Q value, and that's going to equal M times temperature final minus temperature initial times specific heat. But here's what you have to watch. Because of the fact that you're dealing with the system, your delta H is a negative value. So when you get this number and you're dealing with the system, you need to make Q a positive number. Now, when you deal with number 8, the temperature of the water is going to go down, which means it's endothermic, and then when you calculate delta H, that ends up being a positive value. So keep that in mind, please. Anyway, so that's the story, kids. This is going to be due on Friday. If you have any questions, we will go over that during the Google Meet on Friday morning, and I will be sending out a lab tomorrow. So that's the story, kids. Good luck.